Electron configurations, we're going to be talking about that for the lecture today, so I'm not going to really discuss a whole lot about that. A lot of the stuff here is a duplication of what we talked about the last time that we met. So when we talk about electrons occupying orbitals, remember, no more than 2 electrons can occupy a single orbital. All right? Now that's different than an energy level, but only 2 electrons can occupy the same orbital. Now, we could have an orbital that has no electrons or even 1 electron, but no more than 2. Also remember that they have opposite spins if those 2 electrons are occupying the same orbital. Don't get all hung up on whether it's a positive half or a negative half spin. We don't care. We really don't care. Just make sure that they're spinning in opposite directions. And that's what this next statement here, the Pauli Exclusion principle, your Pauli, all right, states that we can't have 2 electrons spinning in the same direction. So on the test, if you should happen to see something with Pauli exclusion, that's what this is referring to, that one of the electrons has to be spinning in this direction, the other in the other direction. Okay. Writing electron configurations. Let's go ahead and get the blanks here first, and then I'm going to take it to the board. We're going to go right to the practice problems, but I want you to have the blanks filled in, and then it might make a little more sense what's happening when I actually start writing it. So lowest energy to highest energy, that's the 1 blank there. Yeah, we're at.
Okay.
Got it? Okay. So again, lowest energy to highest energy. And this graphic I will come back to after we get all the blanks and I start to describe. Yes?
You spelled order.
Spelled what wrong? Order?
Down.
It says order.
Perfect. It's got to be the HTML.
Sure.
This sequence here, if you have a highlighter, I would highlight this. You're going to be amazed that by maybe Monday or Tuesday, this will be a pattern that you're familiar with. Not now, of course, but maybe a little bit later. Isn't that cool? 1S, 2S, 2P. You're not writing anything. All right, Hund's rule, we'll talk about here in a moment. And then we'll work out the practice problems. Okay. And let's go a little further on the blanks. Go ahead and put these in your notes. If an ion has a positive charge, electrons are lost. If it has a negative charge, electrons are gained. Okay. The 5s are part of your homework. Go ahead and put outermost S and P in chemical bonding. Core electrons and 2. The number 8. One for right below alkali metals. 2 right below alkaline earth. 7 right below halogen. And then equal for underneath valence. Then patterns for the representative element ions, full. Again, alkali metals, 1 electron. And that might be it. Oh, nope, there's 2 for alkaline earth. Go, what's that? So 1, lose 1. And then the next blank is 2. And then full underneath noble. You keeping up, Connor? You're not even writing a thing down, are you?
I've written down everything you said.
Dang. Everything that I've said?
Yeah.
So when you just talk right now, you wrote it down.
Alright. And you are going to cross off 6A, cross off 6B.
Oh, sweet. Wow.
Apple,
Whoa.
Benjamin.
Why does that have to be Benjamin? Why can't it be like 5 4?
But the 5s and 6s are your homework. Alright. Everybody get all the blanks there? See? So back up to here. Alright. If you have, and we're not done, oh God no, we're not done. If you have a Sharpie or some way that you can like draw attention to this graphic, or if you want to draw on your periodic table, that's fine.
Okay.
And actually I'm going to blow this up. On your periodic table, and again, you're not going to be able to use your periodic table for quizzes and tests, so I mean you can write on it if you'd like. Right next to the hydrogen here, write a 1. Next to the lithium, write a 2, 3, 4, 5, 6, 7, on down. Those are the numbers, the row numbers. More importantly, those are the energy levels for the s orbital and the p orbitals. Now, what I want you to do is recognize where the s's are located at on the periodic table, where the p's are located at on the periodic table. Okay. We talked about the s orbitals, the p orbitals, the d orbitals, and the f orbitals yesterday. Okay. Remember that? It was yesterday, wasn't it? Yeah.
Yeah.
So when you look at the s orbital, what was the shape again for the s orbital? Sphere, a simple ball, so to speak. Okay. And how many electrons can occupy a single s orbital? 2. That's why there's 2 boxes. Each of these boxes represents where you're going to drop an electron. Okay. When we looked at the p orbitals, what shape did the p orbitals have?
A dumbbell.
Dumbbell. Okay. So it had that kind of figure 8 look. In other words, twice as many spheres as the s's. Okay. But we had how many p orbitals? How many p orbitals did we have? 3, right? So we had 3 p orbitals, and remember, each orbital can hold 2 electrons, so we have 6 boxes to represent the 3 orbitals. Okay. Then when we looked at the d orbitals, how many d's did we have? 5. And how many electrons can we occupy in each orbital? 2. 2. So if I have 5 orbitals, multiply that by 2, I have 10 boxes, or 10 electrons that I can fit in all the d orbitals for a given level. And then the f orbitals, how many f orbitals? 7, very good. And if I can drop 2 electrons in each of those, I'll have 14. Okay. Now, what's really cool when we write out the electron configurations, it's like reading a book or reading a paragraph. I don't care what you want to read. But we always start, at least here in America, we start in the top left and we read across from left to right. America. Okay. Once we get done with this line here, where do we go? Right down here? No, we go to the next line and we read across again. When you get to there, come on back, read across. Okay. Then when we get over here, something interesting happens. I'm not sure if you can see it in the back, but what are the numbers for the s's here? So there's 1, 2, 3, 4, 5, 6, 7. Very nice. And it does the same thing over here with the p's, except there's no 1p because the p's start in the second energy level. And you'll notice that when we look at the d's, where do the d's start at? Third energy level. Now what's funky about the d's are, they're not in the third row. Why? No, they're not special. They just, the D's have more energy. So when we talk about the energy orbitals, S is the lowest energy, then P, then D. So if we move that up and we had the D's here, then it would say, okay, P's have more energy than the D's. No. So that's why we have to drop it down. And some of you think this is how the periodic table looks. Would you agree to that or not?
Yeah.
Actually, the periodic table looks like this. Okay. Notice where the F orbitals are at? They're right here. Okay. In other words, what we did was we slid everything over and stuck them up in there. Okay. So the periodic table really looks like this. Notice how I have the numbers 1 through 7 here, and then I've got my S orbitals, my F, my D's, and my P's are over here. Now helium really should be over here when we do the electron configurations. Yeah, but the reason why the periodic table looks like this is because it won't fit on an 8.5 by 11 sheet of paper. That's why we have to put it like that. Okay. So now, and the same thing applies when we get ready to work an electron configuration. We still go across the row, except notice that the D's are 1 less in the row they're in. The F's are actually in the 6th row, so they're 2 less than the row they're in. D's are 1 less, F's are 2 less. Okay.
So the D's actually start with the closest start.
The D's will start in the 4th row, and the F orbitals will start in the 6th row.
Okay.
And the reason why is because we want to make sure that we actually have it in the right sequence.
Okay.
Okay. Now, on your periodic table, if you want to box these in as the S orbitals, box these in as the P orbitals, box those in as the D's, and these as the F's, nothing wrong with that. Okay. However, you won't be able to use that periodic table on a test. Yeah, Connor.
Could you repeat how many, like you said, 7 F?
There's 7 orbitals for F. Remember, each orbital can hold 2 electrons. 5 for D, so there's 10 across there.
Yeah, what was 2 and
The P's?
yeah.
The P's have 3 orbitals. Remember the 3 dumbbells that go in the X, Y, and Z axis? And then S is a simple sphere. Electron configurations. Okay? Now, let me explain what this represents. Okay? This is an electron, or I even have it called an orbital diagram or electron configuration. What I have is the element with the number of protons. So hydrogen has 1 proton, element number 1. And when hydrogen is neutral, how many electrons will it have? 1 when it's neutral. So 1 negative charge and 1 positive charge. What this up arrow represents is an electron that's spinning this way. If you want to start with your arrows down, I don't care. Okay. For helium, there's 2 protons, so it'll have 2 electrons when it's neutral. So this line right here represents an orbital, so the dashes represent how many orbitals you have per energy level. So the 1s, I've got 1 orbital, and hydrogen only has 1 electron, so it's happy. Helium will have 2 electrons, but I have to put the 2 electrons in the 2s or the 1s orbital before I can start dumping electrons in others. And that's what happens with the lithium. So I fill up the 1s, then I go them over here.
Is that an S?
S, yeah, these are S's, and those are P's.
Is that an L beside the
So are those electrons?
L. This right here,
Yeah.
those are half arrows. The arrow pointing up, that means it's spinning this way.
Oh.
Pointing down, it spins that way. So directional spin.
So it's like, so if you overload on like the first level or whatever, you're only allowed to do so they can get the other, however many you have on the other line, right?
Correct. And we're going to do some configurations here. All right, go to the practice problems, okay, which are right there. Oh, and Hund's rule. I'll speak about Hund when I do the calcium. Looking at the practice problem, we have nitrogen. So nitrogen and the 7. What does the 7 represent here? The protons, the number of protons that it has. So when you are doing these electron configurations, make sure you have your periodic table up. So there's a 7 on there. All right. As we discussed yesterday, when you start an energy level, you always start with an s orbital. All right, start with S. Then when we fill up the s orbital, or if we fill up the s orbital, then we'll start dumping electrons into the p orbital, or orbitals. Once we fill up the p's, then we'll start filling the d's, and then the f's. Now, if an energy level has each of these in here, how many s orbitals can you have per energy level? Orbitals. 1, right? And how many p orbitals? 3. D, 5, 7. And remember, 2 electrons can go in each of those orbitals. Okay, so this is our low energy orbitals. This is our higher energy orbitals. Okay. All right, so with nitrogen, I'm going to start in the first energy level. And if I start in the first energy level, I start with S's. So again, I'm starting at the top of the periodic table. So right here, at hydrogen, that's where we're going to put our first electron in that box to represent it. So, how many electrons can go in the first energy level? 2. And again, I don't care if you start by drawing your arrow up or down. I don't care. It's not that important.
Wait, why? What are we doing?
We're doing electron configurations.
No, but why are we drawing arrows?
They're electrons, remember? The spin, they're directional spin. One's spinning to the right, that way, the other's spinning to the down.
So that's when you draw.
Yeah, this is my plus 1/2, this is my minus 1/2 spin. So it's directional, yeah. All right, so now, if we stopped right there, what would that be the electron configuration for? Which element has 2? Helium, very good, He, there's 2. Okay, so we would drop our first electron here, and our second electron over here in helium. Okay. All right, so now that we have the first row filled, we now go to the second row. Because we need 7 electrons. How many electrons do we have shown so far? 2. 2. So in the second energy level, what orbital do you start with? S. Very good. You always start every energy level with an s orbital. And again, where are the s orbitals located at? Right here. Right here. So I put 1. Now, conversations, keep it down. So we drop 1 electron here, 1 electron here. We filled up that first row. Now we're ready to start the second row. And we start back over here. It's like reading a book. We go left to right. So now we're putting electrons in this second energy orbital. And again, these orbitals right here represent for the S's. Very good. These represent for the P's. These are the F's. And that's what you want to do. You want to have the numbers and the orbitals. So you want to know where the orbitals are at. That'll help you out greatly. All right, so right now we're going to drop another electron in each of those. So now I have an electron here and here, the lithium and the beryllium. If I stopped right here, this would be the electron configuration for beryllium, or Be, for those of you still learning your 52 elements. Okay? Now, as I have the beryllium filled up, I'm going across. Now I'm starting to drop electrons where? In the P's. But what row am I in? 2. So I'm still in the second energy level. So I have 2p. How many orbitals are there? 3. Very good. So I'm going to have 3 dashes. Okay? Now, right now I have 4 electrons. I need how many more? 3. Some of you might do this. I would say don't do that. Okay? According to Hund's rule, it's in your notes there. According to Hund's rule, we want to drop 1 electron in each of the orbitals for a given subset here before we go back and double up. Now, here's the story. Let's say that you have a 3-bedroom house. Now, listen carefully. Let's say you have a 3-bedroom house, and you know what you are. You're either a boy or a girl. Pretty simple. Okay? Now, let's assume that your parents have one of the bedrooms, so it's not one of these, and then there's 3 other bedrooms left in the house. I have a sister. Okay? Now, what would be weird is if I and my sister slept in this room while we had 2 bedrooms empty. Would that be a good idea? Well, we're not in Kentucky, so no, I would say no. Okay? So here in Indiana, we're going to have a bedroom for each until we're forced to double up. Okay? There's a difference. So we drop one electron in each of the orbitals until we have to go back and double up. Now in this case, do we have all 7 of our electrons shown? Yeah, so we're good. If this were not nitrogen, but say oxygen, where would I put the 8th electron? Right there. Okay. Isn't that cool? All right. So getting back to nitrogen. Yeah, don't double up until you have to, until you're forced to. Make sense?
Hold on, I got this.
What do the dashes represent?
Are we talking these?
Yeah.
That's orbitals. So 1 orbital for each s, 3 dashes for each orbital. This is what we call electron diagram with the arrows. Electron notation, the thing right below the next practice problem. How many electrons are in the 1s orbital? 2. So I put a superscript there. How many electrons are in the 2s orbital? 2. Very good. How many electrons are in the 2p orbital? 3. Very good. That is electron. All right, so this is notation. There's a third way of doing this called shorthand notation. Shorthand notation, what you want to do is you want to go to your periodic table and find the element that we're representing, so nitrogen. Go up 1 row and slide all the way to the right. Find the noble gas. So the noble gas just before nitrogen is what? Helium. He. Helium. Okay, that's the, so like nitrogen's right here on the periodic table. We go up 1 row and find our noble gas right here. Okay? When you're doing shorthand notation, go up 1 row all the way to the right, the noble gas. Then nitrogen is in which row? The second row, so we start there and we'll continue our notation. Now, what this represents, the helium, and in this case it's not a very good example. Later, it'll be a very nice example, but this represents the rows above that are filled with electrons. Yes, Connor?
Why do we have 1s and 2s, but we don't have 1p?
Very good. How many orbitals can you have in the first energy level?
2.
How many orbitals can you have in the first energy level? 1. In the second energy level, you can have 4. 1 plus 3 is 4. In the third energy level, you can have 9. 5 plus 3 plus 1 is?
Is this all s though?
No. I'm pointing to these numbers here because that represents S. The 4 represents 3 P's and 1 S. These represent 5 D's, 3 P's, and 1 S. Remember, each energy level begins with S. Each row begins with S. Begins. Again, read it like a book, and it becomes so much easier. Okay? All right. Let's do another example. The one below it says calcium. All right. Calcium. How many protons does calcium have? 20. Very good. Okay. Again, whenever doing this, where do we start? Start at the beginning. Okay. So row 1, S. So how many electrons go in there? 2. Very good. We have the first row filled up. Remember, each box represents an electron. Now that we've filled the first row up, what are we doing? Go into the second row. And what do we start with? S. Very good. We'll drop 2 more electrons in there. Once we have the 2s filled up, we go straight across to the 2. Good. We're still in the second row. And we have how many p orbitals? 3. So we'll do 3 dashes. Okay. And we'll drop 1 electron in each. Okay. Again, make sure you drop 1 in each, and then we'll go and double up. Thank you. Okay. Now that we've filled up the second row, where are we at now? It's the third row. Very good. And we start with S. We'll drop 2 electrons in there. Okay, so now we've got the 3 filled up. Where do we go? 3p. Now you guys are getting it. How many dashes? 3. So we'll drop 1 electron in each. Then we'll double up. Okay. Then where do we go? The 4th row. And start with an S. And how many electrons? 2. Because calcium's the second one in. And how many arrows do we have shown here? 20, which is the same number. Very nice. Okay, so again, when you look at this, read it like a book. Does that make a little more sense?
Yeah.
Okay.
I realize you're looking off the chart.
You have to be looking at the periodic table.
Yeah, I didn't.
Yeah, you always want to look at the periodic table and know, okay, these are my P's, these are my S's, these are my P's. Now we're going to do a D here in a little bit. All right, let's do the notation now. How would I write the notation? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That's sweet.
How'd you get 2 pieces?
How'd I get 2p6? There's 6 electrons in. All right, now for the, and again, this is diagram, this is notation. How would I do the shorthand? How would I do shorthand? Argon? Argon, very good. Again, what you want to do is find where calcium is at on your periodic table. Go up 1 row, slide all the way to the right. And I believe argon's right there. Okay? So what row is calcium in? The 4th row. So we start in the 4th. Now that's a lot nicer than nitrogen's example. Now here's what this represents, the argon. It represents this right here. These are all the rows above. Okay? That's why we always go up here. Shh. Calm down, guys. So all of these orbitals are completely filled. These are what you call the core electrons. And I had you fill that. There was a blank that talked about core electrons. Down here in this row, the S and P orbitals, these guys right here, only the S and P, no Ds. The S and Ps are your valence electrons. You probably talked about valence electrons in junior high. Anybody remember valence electrons?
Vaguely.
Okay, that's okay. But the valence electrons, you could probably, I like to associate valence electrons like the hair on my head. The core electrons, my heart. When these things react, the valence electrons come and go, no problem. That's part of the normal business. You want to cut my hair off? Fine. The core, I'm going to fight you to keep my core, or my heart. Okay? And that's what calcium is doing. Calcium is really hanging on to these guys, these electrons, because it has all those orbitals filled up. And once they are filled up, they don't really want to take them away. All right? So we'll talk more about core electrons and valence electrons when we start doing chemical bonding.
So in the nitrogen, would they still be core electrons then?
For the helium, just in the 1s.
Okay.
Since nitrogen's in the 2nd row, helium's in the 1st row. So that's not a very good example, but
So
it's
just everything that's below.
in the rows above. Yeah. All right. Let's do another example. Make this a fun one. Iodine. And I would write small, somewhere on the margin or somewhere. What is iodine's atomic number? 53, very good. Okay. All right, let's try to do this together. Okay. We're going to iodine, or we're looking at iodine. So where do we start? And iodine's way over here, way down there.
First row.
Start on the 1st row, top left. So 1s. Oh, I'm sorry. Let's do the arrows. So 1s. Put 2 of them in there. Okay. Now we go to the 2nd row on your periodic table. 2s. 2 of those. Slide all the way over to the p's, still in the second row, and we're looking at the p's, which means that there's 3 orbitals. And so if we stopped right there, what electron configuration do we have for? Neon, Ne, right? Ne. How? Because the second row is completely filled up. The first and the second are completely filled up. All right, so now we go to the third row. 3s, good. 2 electrons. Go all the way across to 3p. And there's 3 dashes there. Okay. If we stop there, what is that the electron configuration for? Argon, very good. But we're not to iodine yet, so we're going to keep going. So now we go to the fourth row, correct? Okay. And drop in 2 electrons. Now we get to the fun part. Okay. When we in the fourth row, we are now encountering what type of orbitals? D's. And remember, the sequence goes, the S has lower energy than P, P has lower energy than D. So at this point here, we're looking at d orbitals, but not in the 4th energy level, but in the 3rd energy level. So it's 1 less than the row they're in. And how many d orbitals are there? 5. Very nice. So we'll drop 1 electron in each, and then we'll go back and double up. Okay. And if we stopped right there, where are we at? Zinc. Very good, John. Okay. And then 4p, since we're still in the 4th row, the S and the P's are synonymous with that row. And how many do we put in there? 6. Good. Drop 1 in each before we go and double up. Now where do we go? 5D, or 5S, I'm sorry. 5th row. Then 4D, I heard somebody say. 1, 2, 3, 4, 5. Then 5P. 1, 2, 3. And how many arrows do we need to show? How many arrows? Do we put 6 in there? No, because iodine is 1 away. It's in group 7A. Okay, if we were doing it, if we were drawing the configuration for xenon, then we put that last one in. Okay, and there should be 53 electrons shown here, because iodine has 53 electrons. If you were doing a notation, how would you write it? 1s, 2, 2s, 2, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, okay. Shorthand. Shorthand notation. Krypton, very nice. Again, we're looking for, right there, all the core. So the first 4 rows are completely filled, and if they're completely filled, then we're looking at the same configuration as krypton. Iodine is in the 5th row, so that's where we start. And 4d10, 5p6. Okay. Oh, 5, my bad. Isn't that awesome? All right, let's turn this back on for a second, because we're going to talk about some. What's that?
All the rows that are filled, you take the last element from that row.
That would be the noble gas. That's why I say you go up 1 row, slide all the way to the right, and it's a noble gas. Yeah, Connor?
Why did you put it in the, not the short, the one, why did you just put those in boxes?
Why did I box that in? That represents the krypton. So rows 1 through 4 are completely full, so that's the same configuration as krypton. Okay. Look at, go down a little bit. Okay, here, where it says, and you already wrote this down, if an ion has a positive charge, electrons are lost. Why is that?
Because the protons outran the electrons.
Good, good, very good. So when we look at, say, magnesium that has 12 protons, in its neutral state, how many electrons will it have? 12. When it has a +2 charge, does that mean it gained or lost 2 electrons? Lost. Okay. So it lost those 2. So again, magnesium, neutral. Let's use a pen that actually works. How would I do the electron configuration for this? Good. 1s, there's 2 of those. 2s, 2 of those. 2p, and then 3s, 2, correct? Okay. That's for neutral magnesium. If magnesium gets a +2 charge, what happens?
Just get rid of 3s, right?
We get rid of these 2 electrons, and we'll talk about where they go a little bit later on in the year. All right, so how many electrons do we have? 10. So we have 10 negative charges and 12 positive charges, which gives us a net charge of +2. Okay. One of your homework problems has this. I can't remember the number for sulfur. 16. Perfect. Okay. So again, let's draw it as a neutral first. Okay, so 1s has 2 in there. 2s, there's 2 in there. 2p, there's a bunch there. 3s, and then 3p, where do we go, 4 in. Okay, so that's neutral sulfur. When sulfur has a -2 charge, what does that mean? We're taking away? We're adding. So there'll be 2 more electrons. Now here's what I want you to notice. When you look at the magnesium with the +2 charge, what is this the electron configuration for? Neon. What is this the electron configuration for the sulfur -2? Argon. Notice, and this neon and argon are what kind of elements? Noble gases. So whenever we have a charge on a particle that's a representative element, it will always have the same electron configuration as its nearest noble gas. And when I say nearest, just like with the magnesium, okay, the nearest isn't that way, it's 2 back. For the nonmetals, it's just ahead. Okay? So when this has a charge, when an ion has a charge, it will have the same electron configuration as its nearest noble gas. Do you want to do another homework problem?
Yes.
Like 5C?
Yes.
Like 5C?
I want to do it.
Okay, and your homework 5C, and try it on your own if you don't want to look up here. All right, so on your homework 5C, you have aluminum that has what charge? +3. But let's go ahead and draw it as a neutral element first. So 1s, 2s, 2p, then 3s, and 3p. How many electrons do I drop in there? 1. Very good. Okay. Okay, that's neutral aluminum. Has +3 on there, so what do I do? Take away 3. Which 3? From there and there. And now it has the same electron configuration as who? Yeah, Julie.
Well, I have just a question.
Oh, okay.
Are we supposed to erase like all of it or leave the empty spaces?
You may draw just this if you'd like,
Okay.
or if you want to leave it. You'll always see me write these and then erase them,
Okay.
but that's up to you. So this has the same electron configuration as who? Neon. And that's the nearest noble gas. Okay. Everybody good there? All right, now let me explain. When we talk about valence electrons, I'm talking only about the outermost S and P electrons. So that's what this is referring to, the outermost S and P electrons. Outermost would be the row that the element is on. That's the outermost. Okay? So if I'm looking, say, at, let's throw up the periodic table. Let's say that I'm looking at carbon. Okay? Here's the row. So how many s orbital, or I'm sorry, how many electrons are in the s's for carbon? 2, 1, 2, right? How many are in the p's for carbon? 2. So 2 plus 2 is 4. So there's 4 valence electrons for carbon. Okay? Let's do it for, say, phosphorus. How many s electron orbital, I'm sorry, how many s orbital electrons are there for phosphorus? 2 s. How many p orbital electrons are there for phosphorus? 3. Phosphorus, 1, 2, 3, correct? Phosphorus, p. Okay. So if I have 2 electrons in the s and 3 in the p, how many valence electrons do we have? 5. Okay. Let's do one more. If I look at oxygen, how many s orbital electrons do I have? 2. How many p orbital electrons do I have? 4. So 4 plus 2 is? Now, hopefully you recognize the pattern. That if you go up the column and look at that number, that's your number of valence electrons. If you go up the column, that's your number of valence electrons. If you go up the column, that's your number of valence electrons. Now, the valence electrons only apply to the A columns. These are your representative elements, the S's and the P orbitals. These don't count. Okay? These don't count. So when I ask you about outermost S and P, aka valence electrons, look at the column. Okay? And the valence electrons have significance when we talk about chemical bonding later on, not yet. Already talked to you about the core electrons. Again, the core electrons are those electrons in the rows above where the element's at. And then real quickly, if you're looking at the alkali metals, what column is that in? Group what? 1A, very good. So there's 1 valence electron. In the alkali earth metals, what group is that? 2A, so how many valence electrons? 2. If you jump all the way over to the halogens, what group is that? So 7 valence electrons. And then the noble gases should have 8. Okay. And it states here that when valence electron orbitals are full, the element is unreactive. That's why neon doesn't like to dance with anybody. We'll talk about that later. The configurations we've already discussed, but this is just showing that when we look at neutral sodium and it has a +1 charge, it takes it from that rose orbital. One more thing here, isoelectronic. Isoelectronic. Okay, and then we're done. Everybody pay attention here. Isoelectronic is a term that you need to know. Seriously. Isoelectronic is a definition that states that 2 elements have the same electron configuration. Now, when we were doing it with magnesium with a +2 charge, it had the same configuration as neon. When we looked at sulfur with a -2 charge, it had the same electron configuration as argon. Those have the same electron configurations. They are isoelectronic. All right. Now, remember, protons identify what you're looking at. Electrons tell us what the charge is on the compound, or on the element. So don't get all excited and go, ugh. It just gives us a charge or an ion. Okay. All right, again, for the homework tonight, don't do 6A or 6B. Do the 5s and 6s. Okay. Now I've already worked out a couple of those for you. All right.